Possibly the most important principle of the scientific method is reproducibility. All experiments must be repeatable. This means that it doesn't matter how well your experiment went or how good the results were. If other scientists can't reproduce the same results on their own, something is wrong with the hypothesis. We've been talking about the Keeling curve, the daily measurements of CO2 levels in the atmosphere, and how they've been rising at an accelerating rate. Scientists say the rise in CO2 is caused by human activity, while others say this is naturally occurring as a result of natural cycles. How can you know whether the scientists are right? Since all science is reproducible, you should be able to do the math and get the same results they did. But here's something nobody else has ever told you: the math is actually pretty easy, and you don't have to be a scientist to do it. What we need is to calculate how much CO2 is going into the atmosphere every year, and how much of a percentage of the atmosphere that is. It's just like calculating the percentage of a piece of pie. If the shape of the piece is obvious, then it's pretty easy to calculate. But how can you calculate the size of the piece if it's not obvious? Instead of using its shape, we use its weight or mass. For example, if a piece of pie weighs 1.5 pounds and the whole pie weighs 6 pounds, then divide 1.5 by 6 to get the percentage of the piece, 0.25 or 25%. Scientists often use parts per million. To convert your percentage to parts per million, simply multiply by 1 million. This piece of pie is 250,000 parts per million of the whole pie. The CO2 problem is the same math, except CO2 is the piece of pie, and the troposphere is the whole pie. The numbers are much larger, so we'll need something that can handle big numbers. I'm going to use Microsoft Excel, but you can also use Google Docs or OpenOffice Calc. First, we have to find out how much CO2 is being produced by human activity. Energy companies keep careful track for economic reasons of how much of their product is being sold, so the numbers are easy to find. In this lecture, we'll focus on gasoline. Google worldwide gasoline consumption. This chart shows a graph of gasoline consumed worldwide. For this lecture, we'll focus on 2010. Let's take this number and enter it into the spreadsheet. Since this is in thousands of barrels, multiply that number by 1,000. Now we convert to gallons. There are 42 gallons per barrel, so multiply that number by 42. Multiply that number by 365 and we get 337 billion gallons consumed that year. Finally, we need to know how much CO2 this much gasoline made. Thanks to chemistry, we know that 1 gallon of gasoline produces about 20 pounds of CO2, so we multiply this number by 20. The result is about 6.7 trillion pounds of CO2 produced by gasoline in 2010. This is the piece of pie. Now, a number that we're going to need later is the amount of oxygen that was consumed by burning the gasoline. Chemistry tells us that about 14.5 pounds of oxygen is used up for each gallon of gasoline, so we multiply gallons per year by 14.5 to get 4.8 billion pounds of oxygen consumed in 2010 by burning gasoline. Now we need to figure out how big the whole pie is. The CO2 problem is in the troposphere, the lowest 10 miles of the atmosphere. The mass of the troposphere is easy to figure out, but we don't need to do that here, just Google mass of the troposphere. Google conveniently puts the answer in the first block, which states that the troposphere is between 75 and 80% of the mass of the entire atmosphere. So we Google mass of the atmosphere, and we get a number in scientific notation, 5.1480 times 10 to the 18th. We enter this into the spreadsheet by typing 5.1480 E plus 18. As we know that the troposphere is about 80% of the mass of the atmosphere, we multiply this big number by 0.80. Since we're already using gallons and pounds in this lecture, we need to convert kilograms to pounds, so multiply by 2.20462. This shows us that the troposphere is about 9,000 quadrillion pounds. This is the whole pie. Now we can calculate the impact of gasoline consumption. Since consuming gasoline takes oxygen out of the air, we first subtract the mass of the oxygen from our troposphere. Now we can divide this piece of pie by the whole pie, which means we divide the mass of CO2 from gasoline by the mass of the troposphere. We can adjust the formatting of this number so it's easier to read. To get parts per million, multiply by 1 million. So the consumption of gasoline added 0.74 parts per million of CO2 in 2010. And that's just from gasoline. We need to figure out how much CO2 comes from all types of human activity. So let's go back to the global energy consumption data and take a look at the other items in the left column. If we go through each one of these and calculate their CO2 output, which we will probably do in a future exercise, we can build a chart that looks like this. We can see that in 2010, gasoline consumption was responsible for about 15.81% of the CO2 produced by human activity. Knowing this, we can go back to our spreadsheet and divide the gasoline impact by 0.1581. This means the total CO2 impact of human activity in 2010 was about 4.71 parts per million. We also know that about half of the CO2 being produced will be absorbed over the next year or two by the ocean and plants. We can enter this into the spreadsheet. The final result of our math shows that we have predicted an impact of 2.35 parts per million from the CO2 produced by human activity in 2010. Now we check our math against actual recorded data. Since the CO2 produced in 2010 will take some time to spread and absorb globally, we'll look at the average of the measured rise of CO2 for the following 5 years. According to actual recorded readings, we saw an average annual rise of 2.36 parts per million. You can see that our math agrees pretty closely with actual recorded data. Since there are no other sources for this quantity of CO2, we must conclude that the rise in CO2 is caused by human activity and not by natural causes. Thank you for watching. Please subscribe to our channel by clicking here. Also, if you like what we're doing, please support our project by making a contribution or becoming a sponsor. Visit purescience.com and click on Contributions. Every dollar helps.